Okay, it's time for the sixth and almost last, but not last. We still have one more lecture. So it's about basic statistics, and I would say that the first 5 lectures has actually been some kind of a build up to this, because this is why we're doing this. This is why you're doing this, to get the hang of basic statistics, and then next time we will be talking about confidence intervals, which is a really, really useful, important part of the statistics that you will probably use quite a lot in the future. So let's start. So the main reason we use statistics is to make decisions and draw conclusions about populations. And that could be population of people, of course, but also populations of things. And this aspect of statistics is called statistical inference. And that means in practice, we are looking at diagrams, tables, and you will be using your experience to be able to get an idea about what kind of family of distribution we can use to model this certain situation. Because, okay, we've been through a few different distributions, but they are just theoretical models. They do describe, really in a good way, quite a lot of real world situations, but still, we're talking about a model and real life. So it's not the same thing. We have to kind of connect them in a way that they will be applicable. So when we decided what model, normal, binomial, Poisson, etc., to use, we can then look at our experiments and we can check, is it independent, and so on, and start working by defining a random variable x and go on from there. From now on, we'll then be referring to the independent samples of this variable as x1, x2, etc. This means that the corresponding random variables x1, x2, etc. are independent and has the same distribution. That's the basic idea. So if you, for instance, if you're throwing a dice, you have the same distribution for the dice throw for each and every throw that you do. It could have been that. It could have been throwing a dice n times. And each and every experiment, you know the probability for getting a 1, getting a 2, etc. And in our case, we will be focusing on these two, normal distributions and binomial distributions. Of course, Poisson and exponential, they are interesting, but we will focus on these two in this part of the course because these are the most used distributions, definitely. So we'll be focusing on finding values, estimates, as it's called, for the parameters mu and sigma in the normal case, and n and p in the binomial case. So n is not really a question of doing any kind of approximation or something like that, or estimate, but p is. And the goal is to find functions, to find estimates for the parameters. Okay, so we need to be able to find estimates. Let's deal with some basic estimates. So we'll start with normal distribution. We start with a sample, x1, x2, etc., from a distribution where we have x being normally distributed with an expected value of mu and a variance of sigma squared. We know that mu stands for the expected value. Yeah, that's true. And a good candidate for a point estimate of this would of course be the arithmetical mean, denoted by x with a bar on it, on top of it, and you know how to calculate that. And in order to say that, okay, this is an estimate of mu, we write mu with this little cap on it. Mu cap is the estimate of mu, cap or hat, whatever you want to call it. And it's an estimate based on numerical data, observed data. That's really important. It's not the theoretical value, we already have that, but it's the value that we've gotten from the observed data. Okay, so that's the basic thing about the expected value, how to estimate that for the normal distribution. What about the binomial distribution then? Well, we'll look at this variable x, and we know n, I mean the number of experiments we've been doing, but we don't know the probability p. It has to be estimated from data. But in this case, an intuitive estimate should be p hat equals x divided by n, where x is the number of observations that have the value that we look for. So the number of successes, basically, which is just related to the basic definition of probability. So the number of successes divided by the total number of experiments. So for example, if we have 1,000 components, of which 5 are bad, and we want to get a reasonable estimate for that. So an estimate would be 5 divided by 1,000 being 0.005. So that's just intuitively clear, isn't it? And estimates, they are kind of random, aren't they? So we could look at them as random variables. So let's say we're talking about some kind of distribution, and we have a value, could be the number of dots on a dice. We have some kind of parameter. I don't know, could be p, could be something else. And the available observations, x1, etc., is a sample. And the corresponding random variables are given by this. And they are independent, and they each have the same distribution that I talked about. And you might say, what distribution? Well, we don't know. It's a general kind of distribution. This is just trying to get an idea about how you can look at estimates as random variables. With a point estimate, t, of this parameter, we mean some kind of function that is related to or based on x1 to xn. When we talked about the normal distribution, for instance, we did this kind of point estimate of the expected value, and our function in that case was just this, a basic mean value calculation. This is what I mean. So this is, if you think about this, our basic case with the normal distribution, this thing on top kind of makes sense. Let's look at an example. At a factory, the demand in tons is supposed to follow normal distribution during the period October to March. And the distribution is this. This gives us 6 observations for 1 year, x1, etc., up to x6. And the number of tons are 12, 14, 15, 15, 11, 13. That means if we want to do an estimate for that, of course we will be using the mean value. So calculating the mean value will give me 13.3. So this is a good estimate for the expected value for this distribution. And in this case, it's obvious that the estimated value is dependent on the observed data. We could, of course, do the same for more seasons, and obviously the estimate would then vary. I mean, that's kind of basic, isn't it? So if this is the first season, second season, third season, fourth season, and we have different values all over, of course they will be somewhere around the same value because that's the same kind of factory with the same kind of production. But the mean value, hence the estimate, will then vary over time. And that's exactly what we mean by the fact that this is some kind of random variable that is varying. And in this case, we've decided that it's varying as a normal distribution, and we're using this mu hat as the estimate for the expected value. So obviously the value of mu will vary, just as I said. So let's look at that formula. So the value of our estimate of the parameter theta will vary between different samples. Yeah, we just saw that in the last example, so that's basic. We could then study the corresponding random variable t, called the estimator. This is our estimate. I can then say, okay, if this is some kind of random variable, I could call it capital T and call it an estimator. And the estimator is this function of the random variables in exact the same way as we did with the normal distribution and calculating the estimated value for the expected value. But are we sure that our choice of G from above actually would be the best or even okay? So we have to study the statistical properties of the estimator a bit more. What we need to make sure is that this estimate would on average give us the correct value for our new parameter we're talking about. In this case, this generic one, theta, but it could of course be the mu parameter in the normal distribution. We say that if the expected value of our estimator is actually the value of theta, the theoretical value of theta, then it's unbiased, which is good. It means it points towards the value we want it to point towards too. Obviously, when all our estimate is to be unbiased. So in normal distribution, we know that the expected value of this x is mu. And using our rules on the estimator, so if we now take the expected value of our estimator, which is mu hat, which is the mean value, and we can then calculate that because we know that each and every one of these have the estimated value of mu, and we have n of them, so n times mu times 1 divided by n. So yes, we get the actual value back that we wanted. So this is unbiased. Binomial distribution, does it work? Well, let's see. The expected value of our estimator, which is random variable divided by n, is 1 divided by n times the expected value of x. And we know that the expected value of x is n times p. That's the expected value in a case of binomial distribution. Hence p. Yeah, it adds up because we were looking at the estimate for p and it actually turns out that it is p, which is good. So yes, it's unbiased. So both of these work, and that's good. Now we've been focusing on the expected value, and that wasn't too hard to understand. But what about the dispersion, the spread, things that are in the theory called variance and standard deviation? So we will be looking at the standard error for an estimate. It's called standard error when we talk about an estimate. So let's look at our two distributions and calculate the standard error for the estimates mu hat and p hat. So what about this? Well, the variance for the estimate mu hat is the variance for this. And if you use the rules we've learned before, that means we have 1 divided by n squared times n sigma squared. And if you calculate this, you get this. And what about for p hat? Well, it kind of works the same. Remembering that you have to square what's in front of the value and take the variance for x, which we know is np times 1 minus p. And simplifying that, we'll turn it into this. And that means we get the standard deviations looking like this. Okay, because in this case, we're calculating the variance. And now we're using that in order to get the standard deviation. Okay, but I was talking about standard error. Wait a minute. Yes, because the problem in this case is we're actually using unknown values, sigma in this case, and p in this case. So it's like a bit like a circle, you know, because we're talking about estimates here. And in those estimates, we actually have to use things that we don't know. So sigma and p. So we can't really find the standard deviations, but we can solve it by substituting the sigma value and the p value with the actual estimates. And the estimates, in this case, sigma hat, is the sample standard deviation. And in this case, we have the estimate of p. And if we use them in these formulas, they are no longer called standard deviations, because standard deviation is a theoretical thing based on theory. Instead, we call them standard errors for the estimates. They look kind of like the same, but the difference is here we're using this, which is based on actual data, and this, which is also based on actual data. So that's the difference. Important to remember. There are some other properties of interest also, and these might not be as central to this course as most of the other things we're doing, but I want to mention them at least. A consistent estimate has the property that the reliability will increase as time goes by. So what we actually would like to say is if we do a really huge amount of experiments, the variance should tend to 0 when n tends to infinity. Well, that's kind of reasonable, isn't it? And when we talk about efficiency, so efficient estimate have small variance. So if we talk about two different estimates and we want to decide which is the best, we would then compare their variance, and the one with the least variance will be the most efficient one. Assume that we have 3 independent measures from the same population with expected value mu and standard deviation sigma. Decide which of the following estimates is the best. So this is the basic one. This is a slightly different one, where we've added some weights to the second and the third, and we're dividing with 6 because we have in total 6 x's in some way. Okay, so if we look at, are they unbiased to start with? Well, yes, the first one is, and the second one, yeah. And this, I think you might feel, well, yeah, that wasn't too hard to understand. But what about the efficiency? Well, if I just look at the variance of the first one, using all the rules that I already know, I get sigma squared divided by 3. What about the second one then? I need to, okay, 1 divided by 36 because I have to square everything, and I also have to square what's in front of these, so 4 and 9. So it's 14 over 36. Which is the best? Well, it's actually the first one, because this is less than this. The best one was this. Not to be surprised. Let's dig into a slightly odd example, but this is both fun and interesting. So we have 3 items with weights M1, M2, M3, and they will be weighed on a scale with a precision of sigma. 2 methods can be used. Either you weigh every item once, or you weigh 2 items together, 1 and 2, 2 and 3, 1 and 3. I mean, it's an interesting strategy, isn't it? I mean, which one is the best? And you might say, well, I don't know. Shouldn't be any difference, or shouldn't it? In this case, I'm only weighing each item once. In this case, though, I'm actually weighing the first item twice, the second item twice, and the third item twice. That might be a good idea, don't you think? So let's go on. We'll define random variables where we have the true weight mi and the error epsilon I. And that means in method A, we have x1, x2, x3. Yes, and the expected value of epsilon, all the epsilons, is 0, and the variance for each epsilon is sigma squared, because that's the part that will vary. So when we talked about the precision being sigma, this is kind of the theoretical image of that. We'll just have a peek on x1, and the rest is kind of analog to that. So if I look at the variance for x1, that's the variance for m1 plus epsilon 1, which is the variance for m1 plus the variance for epsilon 1, which is then just sigma squared. So that wasn't a problem, okay? And for x2 and x3 will of course be the same, because they work the same. So, fine. Let's now turn our attention to method B. Of course, the expected value and variance for the epsilons will be the same, and we'll try to just focus on x1 and the rest will follow. So we have x4, which is m1, m2 plus epsilon 4. We're weighing item number 1 and 2, and we have some kind of deviation. We're weighing number 2 and 3, with the deviation, and 1 and 3 and with the deviation. And all the epsilon's expected values are 0, and all the variances for E4, E5, E6 is of course sigma squared. We know all of this. But now let's focus on the first item and create a new random variable being x1 with a small star, just to mark that it is slightly different. And how do I get that? Well, and this might be not obvious, but if you think about it, if you take this one, you take away this one, okay, you still have M1, you have taken away M2 and M3, and then you add this one. The M3 that you took away here is neutralized by this, but then you get one more M1, so you have 2 M1s, hence you have to divide with 2. So this should give you the result x1, kind of. Okay, so if we now look at what it actually means using these formulas, this is what we get. And simplified, this is what we have. So this is what it should be. So it's the weight of x1, and we have a bunch of errors, random parts. That means if we now look at the variation for this one, is the variation for this, which in the end means the variation for that part and that part. The variation for this one is just 0. And in this case, remember, you have to square what's in front, so 1 divided by 2 squared, and then we have to add all of these, because once again you have to add everything, because you're actually squaring the plus 1 and also the minus 1. Okay, so you get 3 of these, and they are the same, all of them. But that means in the end that you get 3/4 of sigma squared in this case. Remember that we had sigma squared in the other case. So this do mean that in this case we get a smaller variance, which is good. So the conclusion is that method B was more efficient, provided that the scale could take that much load, because that's also a problem. If you're weighing items and they are just about close to what the scale can take, and then you can't use this method because you have to put two of them on top of the scale every time. But if it's possible, this is actually a better idea, which is a bit weird, but yeah, it's also intuitive because you're weighing every item twice. And if you look at this, so their error is in some way smaller compared to the weight that you have, because you only have one error because of the fact that it's not the items that contains the error, it's the scale. So every time you use the scale, you get an error. Just you think about that. Okay, estimates of variances then. What about this estimate? Sigma hat squared equals the sample variance. Is it okay to use the definition from before applied to our case? That is, can we prove that the estimate is unbiased? Let x1 to xn be independent observations of random variable x. And as usual, we have the expected value of mu and the variance of sigma squared. So we need to prove this. This involves a bit more math skills than is required in this course. It's not really impossible to understand why this is, and this is actually also motivating why we're using n-1, because the most intuitive thing to do here would be to divide with just n. But it turns out that you need to divide with n-1 in order to get this to work. I won't be going through that. If you want to, you could look it up, you can ask ChatGPT or whatever. If you have taken a bit more math than just in Sweden math 3B, so you have taken, I'd say, at least math 4, you would be able to understand. Might be you need math 5 too, which is kind of like the full range of math for a natural science student in Sweden. Okay, pooled estimates of variances. What does that mean? Well, it's quite common that we have multiple samples to deal with. So let's say we have 3 different samples of observations. So we have this one, we have this one, and we have this one. So as you can see, we have different expected values, and that's one thing. But we also have different sigmas. Often we want to have the same variance for all samples, because that will make things a bit easier to calculate then. And in order to find some kind of a similar variance for these, we will be doing a pooled estimate of the variances. And it's a bit like a weighted average. The strange part here is I'm multiplying with n1 minus 1 times this, and n2 minus 1 times this estimate, n3 minus 1 times this estimate, and then I'm dividing with all of those, n1 minus 1, etc. But this is some kind of weighted average, and the reason we have n minus 1, of course, is because of what we had before. That's the not really formal explanation, but it's kind of like giving you an idea of why we're using n minus 1. And this is just a formula, so I mean, it's quite easy to use. And it's possible to show that this estimate is unbiased and that it can be generalized to more than 3 samples. I won't be showing it now. That's more formal math once again. An example, and I've given you the formula to remember. So let's say we have measured some screws at 4 separate occasions. And I get the first is this one, second, third, and fourth. I want to have a pooled estimate of the variance. So what I will be doing then is, I will going for, 1, 2, 3, 4, 5, 6 values, 6 values, 5, and 5. So that means I'm multiplying with 5, 5, 4, 4. And I will be dividing with 18, of course. I already have the squared values, I can just use them. So this is the pooled variance. And just remember, it's kind of like a weighted average for these variances. If we had put all the 22 observations in a bin and used a normal definition to get the estimate for the sample variance, we would have gotten a worse result actually, being 4.26. So that's just something to think about. So far, we've been saying things like assume that the random variable x is normally distributed with sigma and with mu and sigma squared, and so on. But in real life, how do we actually know what kind of distribution we're dealing with? We don't. The first thing is to decide if a random variable x that we're observing is something that could be Is it a discrete natural number or is it a continuous number? Because we kind of need to decide, is it discrete or continuous? Because there's different models, So let's look at discrete models. If you have independent experiments and the result can only be of two separate values, okay or not okay, success or fail or whatever. Normally, we need to estimate the probability p for one of the results, and n is normally fixed. So this is really, if this is the case, binomial is the best thing. And then we have Poisson. We haven't been talking too much about this, but okay, so Poisson. The first thing you need to remember, it's used to model events that are, in comparison to the time span we're talking about, it's quite rare. It's not happening all the time. It's more like actually random. Modeling the number of rare events during a certain period of time. In this distribution, which is really odd, the expected value and the variance is the same. So this should be approximately true for the sample. So if you have a sample that kind of fulfills the first 2 points, and then you, by using some kind of computer software or something, you realize that the mean value and s squared, if they are the same, approximately, so the variance, this is probably a good idea to use. Dependent on what you're dealing with, this could be a good idea. What about continuous models then? Well, of course, normal distribution is something that we'll be using immensely. It's symmetric around a midpoint. It should be that. Otherwise, it's just not this. Values can be both positive and negative. With that, I'll be meaning positive, negative around the symmetric point. It need not to be positive and negative values, but it should be both above and below this symmetric point. Can be used as an approximation if we have a large enough n. Remember? So this is really, if you're doing something and you're doing it 100 times, you don't actually have to be bothered about what kind of distribution it is. You can always go for the normal one, because if these conditions are okay, you can use this approximation and you will get decent results. So the reason why normal distribution is really important is partly because if you have this symmetrical thing and you can have values both above and below the middle, and that applies to quite a few things, quite a lot of things actually. But also if you have quite a few experiments, so I would say somewhere around 50 or above, or at least if these condition holds, well, you could just go for the normal distribution. It would be a good approximation for you. Then we have the exponential one, of course. It's a bit like the Poisson process, but instead of talking about how many successes we have, we're talking about how long it will be between successes. How long will I have to wait for something to happen, for instance? Only non-negative results, of course, because we're talking about how much time has passed. So it's only non-negative results. It could be modeling time between events we have in the Poisson distribution, or waiting time, exactly like I said. Okay, this is fine, but when we've picked a model, we should always check if it seems reasonable that the model actually models our situation. So how do we do that? Well, there's a few visual techniques, of course. Compare the data to the probability mass density function. Compare the data to the cumulative distribution function. Or you could actually use QQ plots in, for example, R. Let's go through this. Compare data to theory, but in some ways. In this case, we have a binomially distributed sample compared to the probability mass function. And so we have observed shares and we have probability mass function shares. And they kind of line up, I'd say. And in this case, we have a normally distributed sample compared to the probability density function. So this is the orange colored histogram is the actual sample. So observed shares, observed data. And this is, the Gaussian curve. And yeah, it kind of lines up, so it's a good idea to use. But what about QQ plots then? What's that? And that isn't too strange, to be honest. It's an abbreviation meaning quantile in theory versus quantile from sample plot. So we calculate the quantiles for our sample and plot them against theoretical quantiles from the distribution we want to use. In our case, most often the normal distribution. This is not a definite proof that this is the correct distribution, but it's really a good and a quite quick way of checking that your data could actually be normally distributed or some other distribution. Here's two QQ plots with samples that we want to know if they are normally distributed. So these are the two ones. So we have the sample quantiles on this side, the vertical bar, and we have theoretical quantiles belonging to the normal distribution on the horizontal bar. I don't know about you, but the intuition kind of tells me at least that if you have this thing with sample quantiles on one axis and theoretical quantiles on the other, they should line up along a straight line in some way. And if they don't, as in this case, I'd say normal distribution isn't a good idea. But in this case, it's definitely a good idea. So you do it by ordering our sample, calculate the quantiles, and compare the theoretical quantiles to that. Because in order to be able to talk about quantiles and so on, you need to first sort the material from the least to the greatest, and then decide what the quantiles would be. But that's also something that a computer software could do for you. So in this case, the first image indicates that we don't have a normal distribution. On the other hand, the second one says that we might have that. It's a bit shady when you get into the lower and higher parts, but anyway, it feels okay. Let's simulate two experiments then. So we have 20 observations from this normal distribution with the expected value of 25 and the variance being 25, and 20 observations from exponential distribution with the expected value of 25. They have the same expected value, yes. First, we look at the histograms. It's quite obvious that you can see a difference. Okay, this is kind of normal and this is kind of exponential, which it should be, of course. And it's simulated, so it's a computer trying to make it a normal distribution, make it an exponential distribution, and giving you some data, and then it has plotted it also. Next step is to compare both of the samples to the normal distribution in a QQ plot in order to see, okay, and in this case we're trying to see if this set of this set and this set, are they normal distributed? Now we of course know that in this case yes, and in this case no, but how does that look when you make a QQ plot? That's the reason I wanted to show you. So this, yeah, it adds up, and it should. I mean, it should. And in this case, no, I wouldn't say so. So it's quite obvious that if you do this QQ plot without knowing anything, without having done this image from before, and if you just do this, you will definitely immediately say, well, this is not okay, and this, well, it's probably okay. Could go for that. So in this case, we know in advance that the sample to the left is normally distributed and the material to the right is not. But this image, like I say, it's also quite obvious that that's the case. Okay, that was the 6th lecture. And the only thing that's left now is the part about confidence intervals. That's a hugely important part of the course. To be honest, that's kind of like the crown of the course, because that is what you're going to use a lot when you come out there. Because confidence intervals makes it possible to make decisions whether, for instance, you have a factory and you're manufacturing something and you want to improve the process to get, I don't know, lesser faulty products or something like that, and you want to examine, have there actually been any improvement since I checked last? You want to compare two processes and see, is there actually any real difference? And then you can really have a big use for confidence intervals. But that's next time. So until then, bye bye.